message. The deadline for those homework assignments formally still is this Friday. But I promise you that there will be some lenience. I will allow you to hand in on Tuesday. I'm being very careful in formulating the rules because, as you know, I'm not allowed to put a deadline in next week, which is this careers week, and you'll spend all your time on career stuff. So that's why I'm formulated like this, but you get the interpretation. Yeah? Okay. The other thing is that I already invited you to have a look at the description of the case studies. By all means do, because on the last lecture this week, which is Thursday, of course, we will do the assignment of case studies to groups, and the idea is then that you get somehow the opportunity to state your preference, and then of course it's much better if you know what you're talking about. So please have a look, and they're all interesting, they're all really nice. So in that case, if you would say, well, I don't have any preference, I like them all, I would understand, but at least it would be an informed lack of preference. All right. So any other remarks before we start? No? Okay. Then indeed lecture number 10. And for quite a bit of time, 7 lectures in total, we've been talking exclusively about recourse models. But as you remember, when we started out, we learned that there's just one way of looking at the underlying problem, which indeed is an optimization problem, linear program in our case, where randomness appears in some or maybe even all of the data parameters in the constraints. That's the problem we're looking at, and we then learned at the very start of this course that indeed there's also a very attractive alternative way of looking at the same problem, namely the notion of chance constraints. And for today, and actually the next couple of lectures, we'll be focusing on chance constraints. Okay, don't be afraid, we'll return to recourse models. We still need to discuss how to solve them, and in fact we'll extend that notion also to apply to models involving integer variables. We're all aware that in many applications, actually on top of randomness, also integrality is a good thing because it allows us to really model practical problems going far beyond if we do not include integer variables. So that will be a reason. And in fact, we'll also be discussing relation to today's topic, chance constraint models, because I present them as two different subjects. And in fact, if you look in the literature, that's typically how people perceive those two model types as being very distinct, both belonging to stochastic programming, but not really related. But that's, of course, not the full story, and we'll be interested in talking about relations too. So, indeed, recourse models will come back, but for now, we talk about chance constraints. Okay, what is the idea? Well, chance constraints are indeed on the notion of this random optimization problem being a decision problem. Like in the recourse model, we need to decide on our decision vector x before we learn about the realization of those underlying random parameters, the vector omega. And the only thing we know now, at the moment that we take the decision, is probabilistic information. As before, we assume that the full distribution of the random vector is given to us. So that's the information we have, and we need to deal with that, coming up with a reasonable, in some sense, optimal solution X. The idea behind chance constraints is very much addressing the notion of what do we mean by feasibility. Indeed, in a chance constraint perception of the problem, we say, well, we'll call a solution feasible if that random system of constraints is satisfied for sufficiently many realizations, sufficiently many possible futures, given our decision X. And to make more precise that notion of sufficiently many, we actually take into account the information that we do have, namely the full probability distribution. So our translation and mathematical formulation of this idea is to say that the probability of satisfying that system of constraints should be at least at some level. So implicitly, we're saying that somebody should tell us what that level should be. I'm talking about the reliability parameter alpha. That's a number, by definition, in the interval 0, 1, but of course in applications we have in mind that it should be say at least 50%, and if at all possible, even higher. So that's our reformulation of that same underlying random optimization problem, but now in terms of a chance constraint. So what then is the model that we're looking at? Well, here it is. It's, like before, a linear optimization problem in terms of the objective and the deterministic, fixed or hard constraints that we have, generically denoted as equality constraints, but that's without loss, Ax equal b, and on top of that we may have some simple bounds on our decision variables. X should belong to the set capital X, typically non-negativity constraints. Alright, but of course the interesting part is the additional constraint, our reformulation of that number of m typically of underlying random constraints by means of chance constraints. Indeed, it says the probability of satisfying those constraints should be at a sufficiently high level, namely alpha or higher, and only then we call a solution feasible. And well, you know me by now, I'm lazy, I don't want to drag around all that notation all the time. So instead of writing in full the probability T omega x wiggle H omega, I simply write P of x, which will be our definition of the reliability function. This is it. It's indeed that very probability that you wish to constrain. So the reliability function P will of course be important in our analysis of this problem, the chance constraint version of our decision problem. Few remarks are in order. Some of them, of course, I made before. Indeed, if alpha is the minimum required reliability, then apparently 1 minus alpha, its complement, is the risk that we find acceptable. And a good thing about chance constraint models is indeed that those notions, reliability, risk, and so on, are familiar to many people also outside of stochastic programming. That is, if you talk to the problem owners of the application that we're trying to model, they typically can give you some guidance as to what that reliability level alpha should be. And if you confront that with our alternative model formulation, the recourse problem, there appears this whole recourse structure, and the whole notion actually is a bit more difficult to explain to practitioners. So a strong point for chance constraints is indeed this natural concept of modeling reliability or risk equivalently. Indeed, the difference between chance constraint models and recourse problems, if you will, is in what they aim at and what they focus at. Chance constraints are about restricting feasibility. We say on top of the deterministic constraints that we have, X should belong to capital X and moreover satisfy those hard constraints. Additionally, should be such that it is reliable enough. That's our new notion of feasibility. If you confront that with the idea of recourse problems, that's actually going the other extreme way, if you will. It says, of course, you need to satisfy the hard constraints, but beyond that, anything goes. We do not restrict feasibility relative to the random constraints, the idea being that if you do not satisfy it, then you incur costs. And then the recourse model says, well, in that sense, uncertainty comes with a price, and that additional recourse cost, typically expected future cost, appears in the objective as being part of the criterion that we use to decide on the optimal decision. So those are two different perspectives, and both you could say are natural. Final remark is something to be aware of. Indeed, in a recourse model, we observe infeasibilities and do something about it. We have recourse variables that take care of that infeasibility, and we pay for using those recourse variables. So in that sense, a recourse problem is dynamic. It's for a reason that we call those two-stage or multi-stage problems. On the other hand, the model we're looking at now, chance constraints, are static. We now know how it deals with risk. But if bad things happen, the model doesn't say what we do. In that sense, it's static. You could say the world ends. We take our decision, and whatever actually happens in the future, that's beyond our control. It's good to realize that the models are indeed different in that respect too. All right. So, as I mentioned already, our standard assumption in stochastic programming, stochastic linear programming, is always that we know the distribution. It's somehow given to us. And the same thing holds for our adventure now into chance constraint problems, which means that we can actually define the induced feasible set. My notation is that I call it C depending on the level alpha, and it contains precisely those solutions X which are reliable enough. And the good news is that indeed all the ingredients are given to us. In particular, we are given that system of underlying constraints, we are given the dependency on the underlying random parameters, and we are given the distribution of those parameters. So this is a well-defined notion. In that sense, everything is known, but of course that's not the full story. But to be able to solve this problem, we need to know much more. In particular, we will look at what does this notion of an induced feasible set look like? What are its properties, and how can we use those properties in eventually solving those problems, because that's what we are after in the end. So we will be interested in, say, mathematical properties like closeness. Optimal values are attained, and we can actually pinpoint a particular solution. It's not just a limit that actually exists. We would, of course, be interested to know under which conditions we're talking about a meaningful set, a particular set which is non-empty. It's very fine to come up with a beautiful construct to make precise a modeling notion like reliability, but if it yields an infeasible problem most of the time, then let's think again. So indeed, we're interested in that kind of questions. Third property, and in fact that's in capitals for a reason, because that will be the one that worries us most, as we'll learn for good reasons, is convexity of the induced set. Indeed, as soon as we find that a given problem comes with a convex induced feasible set, the problem is nice. Because the other constraints are just linear constraints, it's simple bounds, and the objective is linear. So that would mean that we're looking at a convex optimization problem, and that makes us happy. So convexity will be a key issue, because on the other hand, if we find that, well, for a particular setting, in fact, that induced feasible set is non-convex, we're in trouble. We do realize that solving non-convex optimization problems is much, much harder. Okay, how will we tackle this class of problem? Well, as you're probably expecting, the first thing we'll do is look at a couple of examples. They should help us in developing, posing the right questions, developing our intuition, that kind of thing. And then next time, we'll make it much more general, and in fact, we'll be talking about theory. So stepping away from concrete examples, looking at theory, answering the questions that were just posed. But before we do so, let's reconsider a couple of issues that we know, some of them already are relevant. The first is one of the issues that it says here, discussed in the first lecture, but I think it was actually the second. Okay. It is on the kind of underlying constraints that we can deal with by means of such a chance constraint. In particular, the setting of equality constraints we already know is not a happy match with this notion of chance constraints. And the reason is obvious. Indeed, if the underlying distribution is continuous, then the reliability of a particular solution satisfying those constraints at equality is typically equal to zero. So you could make some very artificial examples where that is not necessarily the case, but that's not relevant for practice. So indeed, for the continuous setting, it's clear that what we will be looking at is indeed then for any relevant level of reliability alpha, that is any strictly positive level alpha, the induced feasible set, that is our set of feasible solutions, will be empty, and that's not very helpful. So from that perspective, it's clear. In fact, also for discrete distributions, what you can hope for is that you pick a solution which indeed satisfies constraints at equality for a particular realization, but that of course will come in an application with a very small probability, and again, for the level of alpha in the range that we are interested in, say at least 50%, again, we will be looking at an empty induced feasible set. So our conclusion is, let me say it again, chance constraints in combination with underlying equality constraints are useless, so let's stay away from them. If you remember, we tried to be smarter than this when we first addressed this issue by saying, well, I can always replace an equality constraints by two inequalities, and we learned that that didn't make things better. Of course it didn't. Yeah, so the message is, from now on, whenever we talk about chance constraint models, the underlying system is consisting of inequality constraints only. And of course, that's a modeling choice, how to do that actually. From a mathematical point of view, I simply always write inequalities of a particular type, namely at least equal to, and that comes without loss. That's fully generic in general, so that's okay. All right, that was the first issue about chance constraints. The next is a modeling thing, namely for this lecture and most of the time in the first two lectures, I was talking about a chance constraint put on top of this full system of indeed inequality constraint. So reliability is defined as satisfying that whole system jointly. And that's why we call such a chance constraint a joint chance constraint. But from a modeling point of view, it's of course also fine to say, well, rather than looking at reliability with respect to this whole system, I'm actually interested in reliability with respect to a single constraint. So on top of that underlying random constraint, I'm going to define its own chance constraint. And that then, in our notation, could be, instead of talking about reliability function B, I'll talk about reliability function B with index I, which indeed is that particular reliability for the underlying random constraint number I. And of course, if I want to do so, I need to have its individual minimum reliability, that is, I need the parameter alpha sub I. And if I do it for all m constraints, then I need m of those reliability coefficients alpha sub I. Okay, that modeling approach is known under, well, at least two different names. The rest of the world calls those individual chance constraints. Here in Groningen we talk about separate chance constraints, and the single reason is that this acronym ICC I need for a different notion later on. So make that distinction clear. I will, if I think about it, indeed use terminology separate chance constraints. And like before, having this reliability function, our induced feasible set is consisting of those variables x for which that reliability is sufficiently high. That is, pi of x is at least equal to alpha sub I. Okay, we do this for each and every of those m constraints. And then, of course, we'll call a solution feasible with respect to all of them if it satisfies all of them at sufficiently high reliability. That is, our solution has to be in the intersection of all sets Ci of alpha I. Okay? Please be aware that the notation might be misleading. I'm talking here, I'm defining a set C of alpha, but by the way I introduce it, we're fully aware that this alpha is actually a vector having m components. Alternatively, I could be talking about C alpha corresponding to the joint chance constraint, where alpha is just a scalar parameter. And a reasonable question is, at least in the notation, they look very much the same. So the deeper question is, are they actually the same? The answer is no. They're not the same. Well, there are exceptions when they, of course, coincide, but typically, no, they're not the same. And it says there, that's one of the exercises, and indeed it was in the previous version of the course where you had the second set of assignments, the second set being on chance constraints. Now we do not have time. Okay. I recall that during one of the first lectures I said, well, if you're really enthusiastic about this course, then Bart and I, recommenders, are willing to give you the opportunity to also do this second set of assignments. This would be one example. Who of you is interested in doing that? Sort of. But the question is, of course, do you have the time? Right. Yeah. Let me know if you're interested, then that's still feasible. But given that you have the over assignment and then the case study to work on, it may be too much. Okay. So, but don't worry. The answer to this question that was dressed up as an exercise actually will be part of one of the next lectures. We'll be looking into the details of the difference of those two ways of modeling and what they bring. The good question is, okay, given that we have a choice as a modeler between joint chance constraints and separate chance constraints, do we have a preference? Well, the answer to that question is, of course, complicated. Namely, it depends on the application. It really comes down to what is it that you would like to model. And in fact, and that's the example given there, one of the case studies, a rather famous, based on a rather famous paper in the stochastic programming literature, is on water management, capturing all kinds of aspects of water management. And there, in fact, both come up, depending on what it is that you wish to model. There are concerns about irrigation and tourism, and it's motivated in the paper why they are modeled by means of individual or separate chance constraints. Then again, there's also the flow in this water system during the entire year. And again, for good modeling reasons, the choice is to model that as a joint chance constraint. So that's the most important answer. It depends on the application, what it is that you actually wish to model. Yeah.
Is it possible in a model to do both separate and
Definitely, yes. And in fact, when we talk about solution methods, I'll also make that more concrete, that's indeed possible. But for now, we're talking about modeling, and then we're not so much worried immediately about solvability. But of course, in the end, we are. Right. Okay. The other matter, and that's actually touching upon this issue, is, okay, as we will see, and that is not really surprising, separate chance constraints are oftentimes easier to analyze and to deal with relative to a joint chance constraint. The reason is, of course, that a separate chance constraint is a special case of a joint chance constraint, namely on a system of one underlying random constraint. So that's a very realistic perspective to take, to say, well, in the end we want to solve those models, and if separate chance constraints are the best we can do, then maybe we should be satisfied in doing that, even though our preferred way of modeling it would be a joint chance constraint. But if that's too difficult, this is how far as we get. Yeah, so that's a very practical answer to that question. We'll return to this issue several times. Final remark before we go to the examples is this. It is important to realize that this nice notion of risk underlying chance constraint is actually qualitative. And I think I need to explain what I mean by that. Indeed, in a chance constraint, we're talking about the probability of satisfying, yes or no, that given system of random constraints. It's only yes or no, and that's actually reflected by our reliability function B, which is a probability, which of course, since it's a probability, is the expectation of an indicator function, and that really pinpoints the fact that it's yes or no, 0 or 1. The point being that in this risk notion, we only take into account, does our solution for a given realization satisfy those constraints, yes or no? And by the amount of which we miss the target, solution. Suppose I'm looking at a random constraint where my decision is my portfolio. And the matrix, which is a vector then, is the returns on that portfolio, and H is the target. For that application, I would probably be interested in, well, by how much do I miss the target? Whereas there are other applications where it's indeed much more realistic to say, well, I don't care about the amount of satisfying or rather not satisfying that constraint. It's really a modeling issue. This idea, this realization that indeed chance constraints are by nature qualitative, is the starting point for yet another class of models that we will be looking at, which try to overcome this issue. That's for later, but for now I want you to be aware that this is indeed inherent to our notion of chance constraints. It's qualitative in this sense. Again, something that we will return to later. Okay, as promised, we'll be looking at examples, learning about properties of those induced feasible sets and what they tell us about the solvability of the problem. Okay, what are we looking at? Well, those induced feasible sets for a given level alpha contain solutions X for which our reliability function P of X is at least at level alpha. That is, our induced feasible sets are simply level sets of the function P, upper level set. So if we want to learn about properties of the set C, it's probably very helpful, if not the same thing, if we learn about properties of that defining reliability function P. So like we've done before, there's always several ways of looking at the same problem, and depending on what it is that you want to know, one perspective is more convenient. So indeed, we'll be talking about properties of the induced set C and or properties of its defining function, the reliability function P. And the relation is immediate. Clear? Okay then. First special case, well, that's just for completeness. Suppose I'm considering to model a chance constraint with reliability coefficient alpha equal to 0. That is, I'm modeling that those random constraints should be satisfied with reliability at least equal to 0. That's not doing much, right? Probabilities are by definition all negative. So that doesn't bring any restriction at all. So it's obvious that in that case the induced feasible set is actually the entire space. No constraint, so the entire space. You should realize that C of 0 is indeed defined to be the set with solutions that are reliable at least at level 0. It's not quite the same thing as a notion that we could formulate as the extremely risky set, namely those solutions for which we are sure that the system will not be satisfied. Well, why we might be interested in that is maybe not that obvious, but it's a different animal, and in fact it will come out later in our analysis. But indeed, induced set is at least equal to a certain reliability. The other extreme is what we might denote as the extremely safe set, and here it is. The extremely safe set says, well, I'm accepting only solutions X for which the probability of satisfying those random constraints is actually equal to 1. It is for, well, F omega almost all realizations of my underlying random parameter, the system should be satisfied. I need to be a bit more precise actually here, what I mean by now the intersection of all sets for omega into support omega, but let's assume that this is all well defined, then this is what we're looking at. For a given realization omega, my system is just a set of linear constraints. Omega is fixed, so T of omega and H of omega are fixed, and we have linear constraints M of omega. Which means that for each fixed omega, what I'm looking at is a polyhedral convex closed set. All right? And now we say, well, it doesn't have to be just in one of them, it has to be in all of them. Again, waving hands when necessary. What we're apparently looking at is the intersection of a lot of those sets, which are each and every one of them polyhedral, convex, and closed. If you take the intersection, the message is that will bring a nice result. In fact, it will be a closed convex set, and if the distribution is finite, then actually it will be polyhedral. So the good news is that looking at this set, the extremely safe set, typically will bring a nice mathematical problem. The downside is that typically those, oh, I'm sorry, I need to go. Yeah, okay. Typically, that set will either be empty, we're simply asking too much, a solution that's feasible in every possible scenario described in the future. Or if it's in fact feasible, then typically we're asking, well, for a very special solution. Special solutions satisfying all those constraints tend to be very expensive. And this idea that we now notice the extremely safe solution is the same thing as what we call the FET solution during one of our first lectures. Those solutions typically are expensive. Okay, so those are two special cases, namely described in terms of the very specific values of alpha. And okay, it's helpful to learn about what we can expect to find, but typically it's not a setting that we will find in practice. Another special case is to say this, okay, let's assume that the problem is actually of a type that makes the analysis a bit easier. Namely, let's assume that the randomness is only in the right-hand side. It is in the vector H, and as before, I'll then say, okay, actually the right-hand side is equal to omega, and the matrix T doesn't depend on omega, it's fixed. Deterministic. Okay, then my reliability function P of x, by definition, is the probability that Tx, component-wise, is at least equal to omega. But that's, of course, the same thing as the distribution function evaluated at Tx. Okay? So if I want to learn about properties of this particular type of reliability functions for this special setting, I need to know about the corresponding distribution function, which is given to us. And that will tell me about properties of P, and that in turn will tell me about properties of the induced feasible set. Why? Because that induced feasible set is simply a level set for that function. Okay, so the induced feasible set, C depending on alpha, contains solutions X for which the distribution function at Tx is at least equal to alpha. Nothing new there. Except that we now realize that we're looking at a set which is defined as an upper level set of the distribution function. Okay. That tells me that if I want to know about convexity of the induced feasible set for all levels of alpha, so anything goes, then actually it would be very convenient to have a distribution function which is concave. Because we all know upper level sets of concave functions are convex. So that would be really great. And we would have found a complete class for which we know, irrespective of reliability level alpha, that it always comes with a convex induced feasible set. That's good news. Right? We're all very happy. Are we? This sounds like a very general result, right? class of distribution functions which are concave. And for all of them, we have this beautiful result. If we're looking at a chance constraint where the randomness is only in the right hand side, we know the induced feasible set is always convex, no matter what the level of reliability coefficient alpha is. Who has second thought? I do. Who of you? You all follow that this indeed is very general. So it sounds like a beautiful result. Okay, let's try to be concrete. Let's try to make an example. Who can give me an example of a concave distribution function? No. Anybody else? What do we know about distribution functions? No. Let's restrict to just the scalar case, one-dimensional. What do we know? It's a non-decreasing function. What else? Bounded. Between 0 and 1, right? Can such a function be concave? No. So we're talking about an empty set. Not very helpful. By the way, bounded functions, can bounded functions be concave? At all? We're talking about distribution functions. But we already agreed that they do not exist. Concave distribution functions do not exist. Can we have a bounded function which is concave? The answer is yes.
Straight line from 0 to
Yeah, constant function you mean. Yeah. Yeah? Okay. Why at all bring up this idea then of a concave distribution function? Well, because this is not what we mean. In fact, there's another notion related to concavity which brings exactly the same result and is indeed fruitful. Namely, the class of quasi-concave functions. Is that a notion that's familiar to you? The one very relevant and proper definition of quasi-concave functions is this. It consists of functions for which all upper level sets are convex. Exactly what we need. And now, of course, the question is, do those distribution functions exist, which are quasi-concave? So we're looking for an example of a distribution function for which all upper level sets are convex. Who can give me an example? Try again. Uniform, yes, correct. Anybody else? What do we know about distribution functions? Let's restrict again to the case of scalar one-dimensional distributions. See a picture of any distribution function on R that's monotone. All monotone functions on R are quasi-concave. So that's a very rich plot, actually. Yeah, so again, a special example, namely special in the sense that randomness is only in the right-hand side, tells us that there's good hope to find also nice settings. In particular, if we're dealing with a distribution function which is quasi-concave, we know that the induced feasible set will be convex no matter what the reliability level is. The message is that apparently solvability, convexity, and other properties depend on properties of the distribution, which if you think about it is of course very natural to find. that's indeed a lesson from this special case. Now, I guess, yeah, the next is to look at concrete examples. And I think this is a natural moment to have a break.